Assalamualaikum and hi. My name is Siti Norabiata Ravia binti Ahmad Nizam. So we are from Group Trifinity. We'll present to you about our report. So first, I'm going to present to you about our task 1, which is task distribution. So first, for Siti Norabiata Ravia binti Ahmad Nizam, which is the team leader, me, my task is to do the division of tasks according to the selected lab by each team members. And then I have to make sure each team members do their task. And then I am in charge of lab 2, lab 8, and also lab 9 for the calculations and also simulations. And then I make sure to keep updated with the team members. And then I also in charge on edit video presentation. And then I will present to you for the lab 2. And then Nur Iman Balkis binti Azman, she's in charge on review the lab report. And then she's also the secretary of the group to record the minutes of meeting. And then she's in charge of lab 1, lab 3, lab 4, and also lab 6 for the calculation and also simulation. And in charge on presentation preparation. And then she will also present for lab 1 and also lab 4. And then lastly for Tirumale Paraja Jaya Lashmi, she will she's in charge of review the lab report, and then she's also in charge of lab 5, lab 7, and also lab 10 for the calculation and also simulation, and also in charge on presentation preparation. And also she's also will present to you for the lab 3.
Hi and Assalamualaikum, madam. My name is Nur Iman Balkis and I'm here to present the results of our Ohm's law experiment where we investigated the relationship between voltage, current and resistor using three resistors. The resistor that being used is 470 ohms, 2.2 kilo ohms and 10 kilo ohms. The aim of this experiment was to verify if the current through a resistor is directly proportional to the voltage across it, which is what Ohm's law states. I will start the presentation with the method and then the results. We connected each resistor in a simple DC circuit and gradually increased the voltage from 1 volt to 8 volt. For each voltage level, we measured both the voltage across the resistor and the current flowing through it using a voltmeter and an ammeter. And this is how we connected the circuit. First, for the 470 ohms resistor, which was actually measured at 465 ohms, and the color coded is yellow, violet, brown, and gold, the current increased from 2.27 milliamperes at 1.07 volt to 70.18 milliamperes at 8 volt. Both the source and resistor voltage values were nearly identical, indicating minimal power loss. Next, for the 2.2 kilo ohms resistor with the red gold color code, the current linearly from 0.455 milliamperes to 3.636 milliamperes as voltage increased from 1 volt to 8 volt. And lastly, for the 10 kilo ohm resistor, the color coded was brown, black, orange, and gold. The current values were small but still followed a linear trend from 0.1 milliampere to 0.8 milliamperes. And this is the graph for all the values. Then I will continue with the analysis and discussion. As we can see just now for the graph, when we plot the voltage against current for all three resistors, the graph shows straight line passing through the origin. This clearly confirms a linear relationship with support Ohm's law, which is V equal to IR. The slope of every graph represents resistance. The 465 ohms resistor had the steeper slope, meaning it allowed more current at each voltage level. Meanwhile, the 10K ohms resistor had the shallower slope, letting less current pass through. This matches the theory as resistance increases, current decreases for the same voltage. Next, minor differences in current readings, especially in the 470 ohms test, could be due to small variation in power supply output, measurement device limitations, or the ±5% tolerance indicated by the gold band on the resistor. Despite this, the trends were consistent and showed excellent agreement with theoretical and expectations. The measured resistor values also align with their color codes, showing our components were correctly identified and within tolerance. So, in conclusion, the experiment successfully validated Ohm's law. The current increased proportionally with voltage for all resistors, and the VL plots showed straight line. The slope of this line matched the resistance values, confirming both our calculation and the theory. Overall, this experiment not only demonstrated the practical use of Ohm's law but also helped reinforce key electrical principles through hands-on application. Now I will pass the presentation to other members. Thank you.
Okay, next, I'm going to present to you for the lab 2, which is series parallel DC circuit. So the objective of this circuit or lab is to compare calculated with measured values of voltages and also current in a series parallel DC circuit. So the equipment required for this lab is DC power supply unit, which is 20 volt, and then a constructor board, and then an ammeter, voltmeter, and also LCR data bridge. So for this lab, for R1, is 330 ohms, R2 is 1000 ohms, R3 is 680 ohms, R4 is 470 ohms, and also R5 390 ohms. So for this lab, we have to measure the quantity of VR1, VR2, VR3, VR4, VR5, IT, which is I total, I1, and also I2. So this is the calculation that I already calculate manually. And also this is the simulation for the lab 2. Okay, so I will explain for the lab 2. This is the table for the calculation and also measured using simulation value. So for VR1, I for the calculated value, I get 5.28 volt. But for measure using simulation value is 16 volt. For VR2, calculated value is 16 volt. But for simulation is 10.67 volt. And then for VR3, 10.88 value for calculated value. And then 5.33 volt for measure using simulation value. And then VR4, 7.52 volt for calculated value. And then for simulation is 5.33 volt. And then VR5, 6.24 volt for the calculated value. And then for simulation, 16 volt. For I total, calculated value is 16 milliampere. And also the same for the simulation value, which is 16 milliampere. I1 is 20 milliampere for the calculated value, but for simulation is 10.67 milliampere. So lastly for I2 is 17 milliampere for the calculated calculated value. And also simulation value is 5.33 milliampere. So the analysis of this lab is to compare measure value of voltages and current in series parallel DC circuit. So this experiment already used 5 resistor, which I already mentioned before. So during the simulation, all the component need to set to its value and place it based on the lab to lab sheet before starting it. In a series parallel DC circuit, resistor can be linked in series, which is end to end, sharing the same current, or parallel across the same voltage, which is splitting the current. The total resistance is measured by combining series and parallel formulas. For series resistance accumulate, our total is R1 plus R2 and others, while parallel resistance use the reciprocal rule, which is 1 divided by R total equals to 1 divided by R1 plus 1 divided by R2 and others. So voltage sources in series add up, whereas in parallel, they must have the same voltage to analyze the circuit. So one would need to clarify the connections. So in conclusion of this lab, through the comparison of actual simulated and theoretical voltage and current values, the experiment effectively analyzed a series parallel DC circuit. So the finding indicate that although theoretical computation gave a good estimate of the predicted behavior, real-world measurement reveals small discrepancies because of things like resistor tolerance, inaccurate instrument, and also small changes in the power supply voltage. Okay, that's all for me. So I pass to Jaya.
So, hello everyone. I'm Jalakshmi. I'll be presenting Lab 3, where we verified Kirchhoff's current law using both practical measurements and circuit simulation. So, firstly, we measured current values in 6 branches of the circuit from I1 to I6. So, using these values, we calculated node currents. That's IA, IB, IC. So, this confirms that the total current entering a node is equal to the total current leaving it in line with KCL. And in addition to the measurements, a multi-sim simulation of the current was also done. The simulated circuit helped to visualize how current flows through each branch in ideal condition. From the simulation, the current values at same branches were observed and used for comparison. So these simulated values closely matches the measured ones, confirming that our physical setup was correct and that KCL holds in both practical and ideal environments. So having the both real measurements and the simulation outputs made it easier to see the accuracy and importance of Kirchhoff's law in analyzing complex circuits. And for the analysis and discussions, Kirchhoff's current law states that the sum of currents entering a node must be equal to the sum of current leaving. So from the calculated values, node A where more current entered via I1 than left via I6. So the net IA was 1.164 milliamp. And for node B, net IB was 5.81 milliamp, meaning more current entered through I4 than exited through I3. And node C, both I2 and I5 entered the node, giving ICS 14.681 milliamp. So in conclusion, this lab successfully demonstrated Kirchhoff's current law through both physical and experimental circuit simulations. The node current calculation matched expected values. Simulation results supported our measurements. So this lab helps us to better understand how current flows in a junction in a circuit and showed how reliable KCL is in circuit analysis.
Now I will explain the results and analysis of our lab experiment on Thevenin's theorem, where we simplify a complex resistive circuit into a Thevenin equivalent. The aim for this experiment was to find the open circuit voltage (VOC), equivalent resistance (ROC), and analyze current values in both the branches and the load. Okay. This is the result and calculations. From the experiment, we calculated the open circuit voltage (VOC) as 10.91 volts, which is the voltage across the terminals when no load is connected. Next, we calculated the equivalent resistance (ROC) or RTH of the network to be 370.73 ohms, representing the total internal resistance seen from the output terminal. When we connected the load, we recorded the load current IC as 7.95 milliamperes. We also calculated branch current, where IA was 4.35 milliamperes and IB was 3.60 milliamperes. The voltage across the load resistor was 7.95 volts, showing that the load received a consistent potential difference. This is the simulation that we made. Then we continue with the analysis and discussion. As we can see, our result is aligned with theoretical expectation based on Thevenin's theorem. The value of VOC reflects the maximum potential available at the terminus when no load is present, while ROC helps predict how the circuit responds to different loads. Once the load was connected, the current through the load matched the prediction using Ohm's law, showing a proper relationship between voltage, resistance, and current. Also, when we look at the branch currents IA and IB, their sum is exactly equal to IC. That proves Kirchhoff's current law, which states that the total current entering at junction must equal the total current leaving. This confirms our circuit setup was accurate and the measurements were correct. Additionally, the simulation results that we got also same as the calculation. This reinforces that our Thevenin equivalent circuit model was valid and practical. Through this, we saw how Thevenin's theorem can simplify complex networks, making it easier to study how changes in load resistance affect the rest of the circuit. In conclusion, the experiment successfully demonstrated how to apply Thevenin's theorem to simplify and analyze a circuit. The values of VOC, ROC, and current were consistent with both theoretical and simulated data. This shows the importance of the theorem in electrical engineering, especially in simplifying analysis and understanding the effect of varying load conditions. It also reinforced key concepts like Ohm's law and Kirchhoff current laws in real-world circuit analysis. That's all from us. Thank you.